Alright, now from here. Okay, now from here we said applying double integral. We've seen our limit, right? We've seen how it works. Okay, now applying line integral. Now the idea is that I'm still using that same curve given. I'm still using when y is equals to square root of x and when y is equals to x squared. But I'm plotting these values of y. Say this is 1. Say this is 1 and say this is what 2. So I'm plotting the value of y when it is 1 and I'm plotting the value of y when it is 2. Meaning when we say 1, meaning square root of x, 2, x squared on this my graph sheet. Me plotting it on it. The purpose is that I want to know the orientation of the curve. I want to know the movement of the curve. You know, from history we said we have a curve, right? And this curve is simply the region, but this region is bounded by C. In what direction does C move? C moves in a counterclockwise direction. C moves in a counterclockwise direction. So what it means is that from here, having drawn my curve, I'm going to move in a counterclockwise direction. So my movement will give me the limit. It will give me the movement of this first curve and this second curve, which will be my limit when it comes to what? Line integral. Alright, now let's plot. For each value of x, I've gotten the corresponding value of y equals to square root of x and y equals to what? X squared. Now for the first one, when y is 0, I'm having this. Okay, let's plot this curve first. When y is 0, I'm also having 0, meaning, and I believe you know how I plotted this graph. But our value of x is ranging from 0 to 1. So this is my x-axis. This is 0 up towards 1.0. Similarly, our value of y is ranging from 0 towards 1. So I'm using this scale. Meaning for the y-axis 0 to 1, for the x-axis 0 to 1. Now, for this first one, when x is 0, for this first curve, when x is 0, y is also what? 0. So I have it here, right? I'm simply starting from here. Now, when x is 0.2, I'm having 0.44. Following my scale, this is 0.2. Then, of course, if this is 0.10, I have if this is 0.2, I have 0.40 between this value, meaning between 0.40 and 0.50. So let's say I have, for this, I have this. This value here is 0.44. Meaning when x is 0.2, y is 0.44. So this is the point. Next up, I have when x is 0.4, y is what? 0.63. So when x is 0.4, when x is 0.4, I'm having 0.66. I'm having 0.63, meaning between this value 0.60 and 0.70. So trace 0.4. Let's say I have 0.60 somewhere here at this point. So at this point, I'm having 0.63. I'm having 0.63. Meaning that I'm having, when x is 0.4, I'm having y to what? 0.63. This is it. The next one, when x is 0.6, I'm having y to what? 0.77. So similarly, I have 0.7 between this region. I have this for what? 0.77 to 0.6. So this is actually 0.6 here. So this is 0.77 to 0.6. Okay, this is 0.6 and this is 0.77. Alright, now for this one I have 0.8 and 0.89. 0.8 and 0.89. So somewhere here 0.89, right? 0.89 corresponding to 0.8. So I have 0.89. I have 0.89. All right. Then lastly, I have 1 to 1. So I have this. So this is 1, right? 1 comma 1. Now from here, join this point, this coordinate, join this point with a straight line. From here, I'm having a curve, right? So let's join. So I'm having something of this nature. Okay. Alright, now from here, the question is this curve that I'm having here, what function of y? This curve that I'm having, what function of y gave me this curve? You observe that when y is equals to square root of x, this is my curve, right? This is my curve. So indicate this curve that you have here, meaning you have this curve when y is equals to square root of what? X. When y equals to square root of what? X. Now, similarly, the same way we plotted for when y equals to square root of x, we are going to plot for when y is equals to what? X squared. Now, 0 to 0, still on 0 to 0, still on this same point, right? The next one, 0.2 to what? 0.04. So 0.04 corresponding to 0.2. I would have it here. Now the next one, 0.4 to 0.16. This is 0.4, right? So 0.16 will be between 0.10 to 0.20. So let's trade it just like the way we did for the first one. So let's say this is 0.16. Next up, I have 0.6 to 0.36. So if this is 0.6, 0.36 will be between this 0.30 and 0.40. So let's say I have it here against 0.6. So 0.36. I also have it here, right? Now I'm having for 0.8. For 0.8, I'm having 0.64. Similarly, 0.8 to 0.64 between this value. So this is 0.63, 0.64. Be somewhere around here. For 0.8. So this is 0.64. Then lastly, we have 1 with what? 1. We have it here. For this, when x is for this curve, when x is 1, y equals to 1. So you still have it here. Now join this curve together as well. Join this curve. Alright, now from here, this first curve, meaning y equals to square root of x. This second one, y is equals to what? X squared. Now we said we want to determine the limit. When it comes to what? Line integral. We want to determine the limit when it comes to what? Line integral. And how it works for line integral is that it's the orientation, the movement of your curve on your graph. This is Green's theorem graphically. You've represented that given question, that given curve. You've represented it graphically. This is graphically. It's what? It followed graphically, meaning Green's theorem. Because from Green's theorem, we said, given any question, you are going to represent that question in a graphical. You are going to represent that question graphically, meaning a closed curve. So this is the closed curve we are referring to. Earlier we said from this table, from what we've evaluated, we already seen that this is the upper limit and this is the what lower limit. So similarly you can also deduce that from your graph. Looking at these two curves, this is the upper limit and this is the what lower limit. This is above this, so we are saying this is the upper limit and this is our lower limit. But now we want to determine the movement of each curve, and we said this curve, this region, say this is R, say this is R, right? Say this is R, and R is bounded. We are relating this curve to Green's theorem. R is bounded by what? C. R is bounded by C, meaning R is bounded by C, right? In what direction does your C move? It moves in a counterclockwise direction. When we say counterclockwise, meaning opposite. When we say counterclockwise, meaning opposite your wall clock, right? Meaning against the direction. So now I'm having, let's number this. Let's say this is our origin. Let's say this is 0, 0. Say this is O. Say this is what? A. Then I want to move in a counterclockwise. I want to move in a counterclockwise direction. I want to move in a counterclockwise direction, meaning I'll move from this curve, meaning 0 to, meaning from O to A, then back towards A. Let's relate it to our wall clock. Let's say this is our wall clock. Say this is 12. Say this is 6. Say this is 3. And say this is what? 9. So I want to move in a counterclockwise direction, meaning I'm moving in this manner. I'm moving in this manner. So that's what we are saying. Meaning for this curve to move in a counterclockwise direction, you are moving in this what manner. You are moving from what 0 to A, and A. You are moving from O to A, and A back to O. So I'm going in this manner. I'm going in this manner. All right. So say this is C1 for this curve represent C as C1. Then for this curve represent C as C2. Represent C as C2. Now from here, ask yourself, since we said our interest drawing all this graph, my interest is that I want to know the movement of this curve. For the value of x, you know, this is the starting point, right? This is the starting point. This is the starting point, and this is what? Ending point. Or you say your finish point. Now, from here, this is where this curve is starting, and this is where this curve is ending. Now, from where it is starting to where it is ending, following the way you are moving, following the orientation of your C, meaning counterclockwise, what's the value of x? You observe that this is x, this is what? Y. This is what? X, this is what? Y. Moving in this counterclockwise direction, you observe that x is moving from what? 0 to 1. X is moving from what? 0 to 1. Meaning for this curve, x varies, or you say x ranges from 0 to 1. Right? Now, for this curve, x is moving from what? 1 to 0. X is moving from what? 1 to 0. That is, you say for this curve, x ranges from what? 1 to 0. X ranges from what? 1 to 0. If you identify the movement of our curve, right? We said the first one moved from 0 to 1, while the second one moved from what? 1 to 0. Now, here, say you want to apply line integral, meaning integral Pdx plus Q dy. Right? Meaning you want to apply line integral to this given question. Just as we know, expected, I'm going to apply line integral, right? I'm going to apply line integral to the first curve, and I'm going to apply what? Line integral to the second curve. Now, meaning from here, I have this is equals to, for the first curve, OA, right? The first curve is moving what? Along OA. The first curve, meaning y equals to s squared. The first curve, meaning that y is equals to s squared, is moving along OA. Is moving along OA. What's the movement of this curve? It is moving from what? X is moving from 0 to 1. 0 to 1. So my limit in this case becomes what? 0 to 1. Then we have this P dx plus Q dy. Then from here you perform your necessary, you substitute, then you perform your necessary integration. All right, now for the second curve, for the second curve, meaning that y is equals to square root of x. In what movement is it moving? Meaning along AO. Meaning along AO. They are moving in this manner along AO. You observe that it is moving from 1 to 0. Both x and y, they are moving from what? 1 to 0. Meaning your starting point is your lower limit. Take note, your starting point, where you are starting is your lower limit. Then when you are ending is your upper limit. What we did for the first curve, we are starting at 0. It becomes my what? Lower limit. We are ending at 1. It becomes my what? Upper limit. Now, I'm starting at 1 for the second curve, which is this. So my lower limit becomes what? 1. My lower limit becomes what? 1. I'm finishing at what? Or you say you are ending at I'm ending at O. My upper limit becomes what? 0. Then you have Pdx plus Qdy. So now, so what this means generally is that all what we've been doing this morning is actually to know the limit. How do we identify this limit? So you are applying line integral. This is your limit for the first curve. This is your limit for the second. Sorry, this is your limit for the first curve, and this is your limit for the second curve. You are applying double integral. Your limit for x and y, just like we've seen before. For your x, 0 to 1. For your y, based on the lower and upper. The lower here is what? X squared, and the upper is what? Square root of x. So this is what we'll be implementing. This is what we'll be implementing when we start solving. Now, from here, before solving, before evaluating, take note that all function of P, dx, Q, dy, everything will be expressed in terms of x. All function will be expressed in terms of x, meaning after expressing all function in terms of x for the first curve and the second curve, then you integrate. And then you integrate, obtain your value. And then you obtain your value, sum it up, meaning you are done answering that question using what? Line integral. Similarly, for this first one, you are going to integrate with respect to y, substitute your definite integral, your lower and upper limit. What you've gotten, integrate with respect to what? X, substitute, you get your answer. So if they are equal, it means Green's theorem is verified for that question. If otherwise, Green's theorem is not verified. So let's see how we evaluate this. Check the description for the link to access the video.